All right. Now we are talking about statistical invariance of Vladimir Vapnik. So there are two approaches to a learning problem. One is minimizing risk functional from observed data that you are very familiar with, especially if you have read the books of statistical learning theory of Vladimir Vapnik. But estimating conditional probability is quite new, and so their definition of risk is somehow different. So we defined the pattern recognition as a problem of estimation of conditional probabilities. So, for example, when we want to classify something, if you're familiar with support vector machine. But before I start, I would like to talk about how measure theory could be related to cumulative distribution function. As you see, this is a measure and this is a cumulative distribution function, which is the integral from minus infinity until a of that probability density function. And so it is quite natural to work with cumulative distribution function rather than probability density functions. So this is a weaker form of convergence in distribution, rather than very, very strict and strong way of convergence in probability. So here you can look at this as a joint probability. So if you have just finite states, you could write this as just a joint probability. So you can write it something like this. Given x, probability of x. For example, if x is finite, you can sum over that. But when it is continuous, you can just replace it with integral. So this is just a probability theory, nothing else. So it turns out that we can write joint probability distribution as a Fredholm, as a first Fredholm equation. We call it Fredholm of the first kind of Fredholm. For example, Fredholm was interested in solving equations of this form. U of x prime is equal to something, for example. And because existence of such functions is difficult, he used a trick of using uniqueness. But we don't need that, just as a historical point of view. And then, so if we write this as a just integral equation, then it could be very interesting, because you can write some empirical approximation of that distribution. So this is a cumulative distribution, but this one is probability density function, and this is the just indicator functions, as you do in a support vector machine. So our goal is to find this one, to approximate this one, because if we know this one, if we know this probability density function, then the finding of classification is just a proper, very, very simple. It would be very simple. So the estimation of condition probability using it is ill-posed, and in order to understand what is ill-posed, I should talk about it should satisfy uniqueness, existence, and more importantly, continuity. Continuity means that if, for example, there's an operator acting on our Hilbert space, then it goes to Hilbert space as well. But this is, for example, f of x. So if f of x, if this one varies a little bit, just a little bit, for example, a little bit, this one should not vary too much. So that should be vary just a little bit, not a sudden jump and completely new probability. So this is the idea of continuity. And it turns out that if we use just some regularization and we use Tikhonov regularization method, then we can somehow weaken this risk function, and we can have a unique as well as we can prove that this has a unique solution, and we don't have any problem. So we just write the risk function as this distance, but this distance is just L2 metric, so we can write it precisely as an L2 norm. So it's just an L2 metric in the reproducing kernel Hilbert space. So we define the risk as usual, as we did. If you're familiar with V matrix in theory of Vladimir Vapnik, then it's just the risk. But here we find that we can define these f as before. We can use some kernels. These kernels, we can use these kernels, and you can find this norm. So we write the norm as so we calculate the norm of reproducing kernel Hilbert space as we use a inner product to define the metric. And so we just need to understand A is the L-dimensional vector. If we understand A, then everything is complete. So instead of this, we can write in this matrix form, and you can write the metric as like this. So our risk function, we want to minimize it. We have minimized it in a support vector machine, but now we use V matrix. So the idea is like this. For example, I talk about a regression problem. If something is here and you are minimizing it like this, you're minimizing the least square. So not only you are reducing the residuals, these are residuals, but also you take care of the distance between your training data. So V comes here. So the distance also matters. And you see that we define, I will explain that we define some predicates, and we define it, so it's just a weaker form of convergence, weaker form. So if we define psi such that this becomes a constant, then we can consider estimates of py equal to 1 given x, which we are interested in. So this is the stronger mode we use. For stronger way of convergence, we use metrics. But if we go and do some, if we use inner product, you can talk about some weaker way of convergence, as here. This is just a weaker way of convergence that I will talk about. For example, we want to know if P and P minus PL, which is approximation of that, and psi, if this goes to 0, then L goes to infinity. So this is a weaker convergence of PL through This is true probability, and so we define those. We approximate it. We can easily approximate it using just simple trick, and so we have some equations, and so we can write your risk function like this. This is your risk function, and these are the invariants. So we use some predicates. Those size, these are predicates. You know, it's a weaker way of convergence. So we have this formula, and I will show in the next lectures that A can be written as sum of two terms. So we call this data-driven. This is data-driven. We just use the data. And this is intelligence-driven, which is given by, so you know, in teacher-student model, we are talking about that it takes a long time for a student to develop a theory, but if a teacher says some experiences that he has had in his life of research, then this student can find the global points of those optimization problems very much quickly, and he can understand that very quicker. So this is the idea of intelligence. That's why the rate of convergence goes very fast. So instead of training millions of parameters of neural networks, we have some experience from this teacher. So we represent it with some psi functions in our weaker approximation, and so our results will be much faster. And thank you.